Thanks, Chen Ke. And also, I would like to thank the organizers to putting together such a wonderful program. And so today I'm going to talk about Fermi surface anomaly, which is based on some of our recent works here. I would like to introduce my collaborators, Dachuan Lu and Meng Zeng. They are both at San Diego, my students, and my long-term collaborator, Zhuwen Wang. So it's about Fermi liquids. Fermi liquids are gapless phase of fermions in many-body systems. And then it has a Fermi surface, well-defined quasi-particle at low energy. That's all we are all very familiar with these ideas. Despite of its long history of study, there has been renewed interest on Fermi liquids or non-Fermi liquids. And one question is basically what is protecting the gaplessness of the Fermi surface. So as we have heard during the conference and also in the program, there's maybe some recent trend of trying to understand gapless quantum phase of matter from the emergent symmetry and symmetry anomalies associated with maybe a higher dimensional bulk. So the idea, for example, we have seen examples in deconfined quantum criticality, which has an emergent anomalous SO5 symmetry. And then maybe there's 2D Ising criticality, has an emergent anomalous Kramers-Wannier duality, which is actually a non-invertible symmetry. And then Dominic yesterday also talked about Fermi liquids. One can view that as there's an emergent anomalous LU1, loop U1 symmetry. One way to understand the anomaly, quantum anomaly associated with symmetry, is to view the system with anomalous symmetry as a boundary of some bulk system, where the bulk system doesn't have the symmetry anomaly. Instead, it is a symmetry-protected topological order. And then we wish to apply this kind of idea to Fermi, to understand Fermi surface. Of course, I'm not claiming that our point of view will fully solve the problem, but we try to move along this direction and see what we can get. So if we want to ask what is the bulk of a Fermi surface, because the Fermi surface is the system that is gapless, but the Fermi sea is like the bulk of the Fermi surface. If you ask any undergraduate student in the condensed matter physics course, they will answer that, of course, the bulk of a Fermi surface should be the Fermi sea. But what is topological? Because we wish that there must be something topological in the bulk in order to protect this gaplessness on the surface. But if you ask what is topological about the Fermi sea, and it was realized by Daniel and many other people that actually Fermi sea can be viewed as a topological insulator or Chern insulator, but not in the real space, instead in the phase space. So one toy example to understand this statement is to look at 1 + 1 dimensional Fermi liquid, where you may consider a free fermion system in 1 + 1D with some dispersion relation, such that the fermion occupy all the way to the Fermi surface at momentum kf and minus kf. So this is the picture in the momentum energy space, but if you try to move to the phase space, which is the space spanned by the coordinate and momentum, and you ask, well, in which region that the system is occupied by fermion, then the fermion occupies from minus kf to kf in the vertical direction and occupy the whole system in the horizontal direction. And from this picture, we also know that there's a left moving mode right moving mode at kf and left moving mode at minus kf. So if you plot that in this picture, then if you look at this picture, it really looks like the boundary states of a Chern insulator. So in that sense, Fermi liquid in this one-dimensional system looks like a Chern insulator in the phase space with chiral edge modes running on the boundary of on this momentum boundary. So so we try to formulate this phase space Chern insulator. Maybe we can write down an effective low energy theory for that. So we can learn from the Chern insulator formulation in the real space. So if we want to formulate an effective fermion theory for Chern insulator in the real space, we can start from Dirac fermions and then add a mass term, such that this field theory describes fermion field at every point in the real space, x and y, if I consider a two-dimensional system of ordinary Chern insulator, then I can have a profile for my mass term. Maybe my mass term is negative in one region and positive in the other region. On the mass domain wall, I would expect to see these chiral fermion modes. So this basically describes a piece of Chern insulator in the field theory in the real space. So in order to move to the phase space, I think one very straightforward idea is to replace every y direction by the k direction, by the momentum direction, and write down a theory like that. Then you would try to say that, okay, then I can define fermions at every point. But hey, wait, there's a subtlety here, because we know from quantum mechanics that momentum and coordinate, they don't commute with each other. So you can't really quite say that how do you define a fermion field at every point in the k space, because you can't measure the momentum position precisely simultaneously. So this phase space Dirac fermion is actually a non-commutative field theory, meaning that it's a field theory defined on non-commutative manifold. There are many proposals how to treat this non-commutativity between these coordinate x and k. One idea is to expand around the commutative limit by Moya product and things like that. And there's also non-perturbative treatment. I think there are two different ways. One is to consider that x and k still commute with each other as ordinary coordinates, but unfortunately there's a uniform magnetic field in the phase space, and the magnetic field has a curvature, Berry curvature, which is dx wedge dk, such that it's uniform and of order 1 everywhere in the phase space that impose this canonical commutation relation. Another way of resolving this canonical commutation relation is by canonical quantization, meaning that you treat x as a derivative of k and k as derivative of x. I think both of these approaches will be useful in defining or make sense of this theory. But let's maybe first take the first approach where we consider that in order to describe a Chern insulator in the phase space, what we need to do is write down an effective theory of fermions, and then where we replace every partial differential equation operator by this covariant derivative with a Berry connection. And then this Berry connection will have a curvature in the background curvature in the phase space. And then there may be a mass profile which specifies which region is occupied by fermion, which region is not. So supposedly this M will be negative from minus KF to KF. So that could be a bulk kind of theory for the phase space Chern insulator. And because of the introduction of this background Berry curvature in the phase space, then we can treat x and k as if they are commuting with each other. So then at this point, we can basically integrate out the fermions and obtain an effective response theory. And this response theory will be in terms of the background gauge connection that we introduce, and then it will be a theory in the space-time, or maybe we can call it phase space-time, which contains coordinate x, k, and also the time t. So it will. Yeah. Integrating over the txk space. Yes. So that's why it's a 3-form here. And then this level is only non-trivial, only non-trivial within the bulk of this Chern insulator, which is between minus kf to kf. So if you have such a theory, you already can see this response theory captures the very essential aspect of Fermi liquid, which is the Luttinger theorem, essentially. Because if you start from such a Chern-Simons theory and try to compute what's the fermion filling or the charge density, what we need to do is to take the action and take a derivative with respect to the gauge connection in the temporal direction, which in order to obtain the density of the fermion. And then if you do that, one can see that immediately give you this the curvature in the x and k direction integrating over the phase space. And that integration will naturally give you a volume of the Fermi surface, because it's a uniform curvature in the phase space, and the volume of Fermi surface, the volume of the Fermi sea will be proportional to the size of this Chern insulator in the phase space. So that basically says that this Chern-Simons theory is describing a response which is very universal, which tells you the fermion filling is tied to the volume fraction in the momentum space. Yeah.
So the x and k here in this information appear kind of on equal footing.
Yeah.
It seems like so. Then does this imply something about taking the soliton and position space rather than momentum?
Yeah, then you can take it either in the position space or momentum space. You should expect if you take the solitonic mass in the if you take the mass domain wave in the position space, there will also be a chiral mode there. But that basically means that if you hit the boundary, there's an electric field on the boundary that will pump the fermion from negative momentum to positive momentum. That's exactly what you want. If you apply an electric field to a fermion system, to a Fermi liquid that exactly pumps, that moves the fermion from minus K to K. That is the chiral edge mode on the position space boundary. Yeah, yeah. Okay, so these are the basically, I'm just talking about a toy model, and then it seems that it can lead to some Bock-Chen-Simons theory, which is quite reasonable, and then it captures the very essential response theory in the Fermi liquid, and this has been discussed in many of the previous papers. And this idea has also been generalized to higher dimensions. You can consider two-dimensional Fermi C with a one-dimensional Fermi liquid, Fermi surface. In that case, the phase space-time dimension should have two-dimensional real space, two-dimensional momentum space, plus one-dimensional time. So the total dimension of x and k and t is 5 dimension. That's why we can write down a 5-form Chen-Simons theory in that dimension to capture the response, essential response of 2D Fermi surface, let's say. So I want to talk a little bit more about this two-dimensional Fermi C with a 1D Fermi surface, let's say. So this is Chen-Simons response that we just mentioned. And then this basically is supposed to be the bulk theory of a Chen insulator in this phase space. And then this is the response theory, and then we expect that this theory will source the anomaly on the boundary. Well, the boundary of the system is this one-dimensional Fermi surface, of course, together with other spatial dimensions. So the boundary, if you look at this 5-form Chen-Simons theory, the corresponding anomaly looks like a 3 plus 1D wild fermion, because this is like a 4 plus 1D. Its boundaries should be like 3 plus 1D. So the Fermi surface, if there's any symmetry anomaly on the Fermi surface, probably it should look like a chiral anomaly of wild fermions, which Z classify under U1 symmetry. And this has been explained in also papers by Chong. And then, and this idea is basically saying that if you preserve the U1 symmetry of the fermions, and then there should be a Z classifier, means that if you have U1, and also another thing I didn't mention is that actually there's an emergent LU1. You can also derive that along the Fermi surface, and then that actually contains both U1 and translation symmetry, and protected by those symmetries. The Fermi surface, you can't gap it out trivially, no matter how many copies you make. So that's the meaning of Z classification. And then around that time, I was visiting Harvard and Mitch Juven, and then he asked me a question about what if in the previous discussion, if we break the U1 symmetry, I mean this U1 is a global U1 symmetry, charge conservation symmetry of the fermion down to its Z4 subgroup. Because Juven is very obsessed with all these kind of non-perturbative anomalies, and he knows very familiar that if you break the U1 down to Z4, the classification of anomaly will reduce from Z to Z16. And then this basically means Z4 symmetric wild fermions can have a trivial gap phase driven by the interaction when there's 16 multiple of the fermions. So the idea is whether we can see similar effect of this, this gapping after 16 multiples in two-dimensional Fermi liquids with one-dimensional Fermi surface, because we suppose that this is the bulk theory for that two-dimensional Fermi liquid. So maybe this argument can go through. So, so that's the question he posed to me. Does the Z4 symmetric 2D Fermi liquid also require 16 multiples to be trivially gapped? Yes. Yeah.
So that momentum space
yeah.
thing with a magnetic field in the xk.
Mm.
So if I really just take that model with this domain wall for the mass and solve it, do I get the right spectrum?
Yes. In our paper, I skipped this part. But even you can take this model in higher dimension, and solve the equation of motion for fermions, you precisely get the chiral fermion modes on every momentum point at the Fermi surface, pointing along the normal direction. You can show that. Normally you don't expect that. You expect chiral fermion mode to move on along the tangent direction of the surface. That's our normal intuition of topological insulator. But this is no longer the case here. It's because of this non-commutativity between momentum and position, and you need to solve the equation in a way that is not conventional. Yeah, you can put. Yeah. To confine the fermions to every momentum point on the Fermi surface independently, such that there's no tangent motion of fermion along the tangent direction of the Fermi surface. One can show that, yeah. Okay, so Druven posed this question about how, if we break U1 down to Z4, whether there's also Z16 classification, and I thought about it a bit, and I say this cannot be true, because there's a counterexample where I can show you that you just need fourfold of the Fermi surface in order to trivially gap out this system if you only wish to preserve the Z4 symmetry. Because I can explicitly write down a Hamiltonian, in this toy model, I have some fermion hopping in these two-dimensional systems, and in general, the hopping term will generate some Fermi C with a fourfold degeneracy. Then on every site, I can turn on an interaction. The interaction is like a charge 4E superconductivity that is simultaneously annihilating the four flavors of the fermions on every site or creating it. So in the weak interaction limit, we have a fourfold degenerate Fermi surface. However, in the strong interaction limit, when G goes to infinity, the system preserves the Z4 symmetry, but it has a unique ground state, which is a superposition of all 0 and all 1 states on every site independently. You just product them together. This product state is a trivial gap phase, and then it can be connected to this fourfold Fermi surface, which means by anomaly matching, the Fermi surface anomaly must already vanish at multiplicity of 4, not 16. So what's going wrong with the previous argument that from the Chern-Simons theory perspective, the Fermi surface anomaly of a 2D Fermi liquids looks so similar to a wild fermion, but its classification is not 16, but 4. The problem lies in the incorrect dimension counting. Because if we consider this phase-space Chern insulator, we try to classify the phase-space Chern insulator. Actually, here is the problem. And then should we consider the D plus 1 dimensional phase-space Chern insulator, which D correspond to space, this D correspond to momentum, and then there's 1 correspond to time. Is it like a topological insulator classification in 2D plus 1, or actually D minus D plus 1, which correspond to 0 plus 1 dimensional classification? We need to think about this question more carefully, because this lies in the fact that there's a non-commutativity geometry in the phase space that the position and momentum don't commute. So another way to resolve the non-commutativity between position and momentum is, you can say, in any D dimension, I can write down, first of all, formally write down a Dirac fermion kind of a Hamiltonian, where I have a position and momentum term here. But then, due to the non-commutativity between position and momentum, one way of canonical quantization is to replace every momentum derivative by a position operator. So if you do that, this effective theory actually is not describing a D-dimensional system. Instead, it's actually describing a 0 plus 1 dimensional system, because this X term coupled to a gamma matrix actually anti-commute with the derivative term coupling to the other gamma matrices, and eventually this actually imposes a sequence of intersecting domain walls in the system, and then eventually localize all the low energy fermion down to a single point at the origin of the system. So the low energy effective theory of this box theory is very simple. It's just some fermion modes at the origin. And this mass basically tunes the topological transition in the so-called 0 plus 1 dimensional bulk. And the bulk state can be trivially gapped if there can be some interactions that can symmetrically gap those fermion 0 modes at m equals 0. M equals 0 correspond to the SPT transition point. So if you have fourfold degeneracy on the Fermi surface, and also you respect the Z4 symmetry of the fermion, then there indeed exists a trivialization interaction which corresponds to this, again, charge 4e superconducting like a pairing kind of a term, which can lift all the degeneracy at the origin, which means you don't need to go through any phase transition, bulk phase transition, in order to tune from trivial to non-trivial when you have multiple 4 of the Fermi surface, which means that the Fermi surface anomaly must vanish when you have fourfold Fermi surface. Yes.
In the previous slide,
yeah.
Maybe even further.
Yeah.
Yeah, I wonder if, so here you consider large change. But suppose you require that the Fermi sea at the depth is not modified by the perturbation, and you still gap on the Fermi surface. So that's in that limit, you cannot take G go to infinity, because G go to infinity affect Fermi sea, deep Fermi sea. So here the question is following. Whether you can design interaction only along Fermi surface without affecting the deep Fermi sea, well, that interaction can still gap off.
Yeah. That's a very good question. So this is more like a dynamical question, meaning that as I turn on this G and stronger, does the somehow gapping happens near the Fermi surface, or it undergoes some intermediate phase transition?
So maybe really is that here the G is on site. Suppose you mix near out.
Yeah.
So the G only couple nearby momentum.
Yeah.
So maybe you can design interaction to not affect.
I will provide you.
The anomaly anomaly argument may require you have an impact Fermi sea at the depth. And if that one is not affected.
Okay,
maybe,
I see.
I wonder whether in that limit you might have a Z16.
Okay.
Following up on Shaolan's question, right? I mean, you can think of your space-time geometry, right, along x and k.
Yeah.
K direction is finite, right?
Yeah.
Like kf is finite.
Yeah.
So then, the boundaries start to talk to each other.
Yeah.
So
I see. Yeah, that's fair. Yeah. So yeah, that's a very good question. But suppose there's a direct continuous transition from Fermi liquid to this gap phase. Then at the transition point, we can say it's a low energy. So we are imagining that there is such a transition, and we don't know yet. But then, if there is such a transition, then everything can go through on the field theory level. Then we should be able to match the anomaly by this kind of approach. Yeah.
So suppose that you have non-trivial instability.
Yeah.
That changes the symmetry of the Fermi surface. It doesn't get it out.
Yeah.
So how will it look like in your language?
Then you will have your Fermi surface anomaly is still there. I mean, it's how. Then in that case, you maybe change the Fermi volume or something like that, right? Or you move some. Okay, so that is not part of the consideration here. Yeah. Your mass turn can have different shapes, but here we are specifying the mass turn has a certain shape. Yeah. Okay, so that was our understanding that actually this effective theory is not in D dimension or 2D dimension. The momentum space dimension in this effective fermion theory should be treated as a negative dimension for the purpose of SPT classification. We know that SPT classification of fermion systems is very sensitive to the dimension, maybe spatial dimension of the system, and then the effective spatial dimension you use to plug into the SPT classification formula should be the real space dimension minus the momentum space dimension. The momentum space dimension can either be can also be interpreted as a parameter space dimension or synthetic dimension, which has been discussed in many previous works. And in particular, Chaoming and Chen Ke's previous work show that this kind of a dimension reduction basically formula, it is not only a free fermion level kind of a phenomenon, it also applied to interacting fermions. So what I just provide you is a free fermion derivation by on the free fermion level, but we can use the result there to generalize this conclusion to interacting fermions. So with that, one can try to classify the Fermi surface anomaly by looking at this bulk theory, where the bulk theory actually has a d minus delta dimension. And then if we are in a three-dimensional real space, assuming U1 symmetry, then this delta can be controlled by the Fermi C dimension. So for example, if you have a regular Fermi surface in 3 dimension, where the Fermi C is a 3 dimension and the Fermi surface is 2 dimension, which has codimension 1, then d minus delta is 3 minus 3, which is 0, then the classification should match the 0 plus 1d classification. However, in 3-dimensional momentum space, there can also be cases where you can have Fermi rings, or maybe you can have wild points, and in those cases, the Fermi C dimension effectively will change, and then that will lead to different classifications. So in the end, our understanding is that the Fermi surface anomaly can be viewed, can be calculated maybe using a formula where there's an integer part, which is the index, where the index is coming from this classification, belongs to the classification group, and then it is associated with the multiplicity of the Fermi surface, maybe the charge assignment and things like that, and then there's also the volume fraction. So together, if you multiply the index with the volume fraction and summing over all the Fermi surface, if this number is not 0, not 1, then there's a Fermi surface anomaly. That's our understanding. And then if you can cancel this anomaly, then it is possible to gap out the Fermi surface by interaction effect without spontaneous symmetry breaking or topological ordering. So, that leads to a concept of Fermi surface symmetric mass generation, which is specifically the phenomenon that when this index magically cancels between different Fermi surfaces, and then it becomes possible to design interactions to gap out the system without breaking symmetries. Yeah.
Like a definition of a Fermi surface for this context, do I need to have a discontinuity, or can it be some non-elasticity in the distribution?
Yeah, I think the idea to compute this index is you always go to the free fermion limits, let's say, and then try to match the anomaly there. Where, yeah.
Okay, so you need discontinuity.
Yeah.
This condition is like integer number fermion per unit cell.
Right. Yeah, it's basically charge compensation condition. So we can consider a very simple toy model, which is 1 plus 1d, and then which exhibit this phenomenon. Well, the model has 2 flavors of fermion. One I call A, the other is B-type fermion. So the A-type fermion, so the system has a U1 symmetry. And then the A-type fermion is charge 1 under the U1 symmetry. And the B-type fermion is charge 3 under the U1 symmetry. But A-type fermion has an electronic band or pocket, which has a Fermi volume 3 times as the B-type fermion, which has a whole pocket whose Fermi volume is just unit 1. So in terms of KF, their KF is a 3 to 1. In terms of the charge, their U1 charge is 1 to 3. If you have a system like that, then it actually cancels the Fermi surface anomaly, because the anomaly now you take the index is set by the charge, and then the Fermi volume fraction is set by the KF Fermi momentum, and then if you compute them, because they are 1 over 3 and 3 over 1, so they compensate with each other. So in the end, there's no Fermi surface anomaly, meaning that there should be a way to gap out this system without breaking the translation symmetry and the U1 symmetry. However, you can see it is not possible to do that on the fermion bilinear level, because on the fermion bilinear level, the only way to remove this gapless fermion on the Fermi surface is either you open up a superconducting gap, breaking the U1 symmetry, or you open like a charge density or whatever density wave gap, but that will break the translation symmetry. So in the presence of U1 and translation symmetry, it seems that there's no way to gap out the Fermi surface in this situation. At the fermion bilinear level, however, the anomaly cancels, which means you must be able to gap it out by interaction. And then there is indeed an interaction that does this gapping, which is written in this form. It's a 6 fermion interaction that involves simultaneously annihilating like 3 fermions of the A type on the neighboring 3 sites, and then creating fermions or annihilating fermions on these sites. It looks very complicated, but one can check that this interaction indeed preserves the translation and U1 symmetry, and actually also preserve a lattice reflection symmetry, which is denoted as Z2 here. And then what is the designing principle of this interaction? It turns out that the way to design this interaction is to look at the low energy theory of the one-dimensional model. If you try to look at those left and right moving mode of fermions near the Fermi surface, one can define 2 U1 symmetry at low energy. One is the so-called U1 vector symmetry coming from the global U1 conservation. The other is the translation symmetry becomes an eminent U1 symmetry, which people sometimes call U1 chiral. And then here are the charge assignment for all those modes. So like A fermion is charge 1, B fermion is charge 3, but in terms of momentum, they carry different momentum at different momentum points. And this charge assignment is such designed that there's no anomaly in U1 vector or in U1 axial or in their mixed channels. So there's no anomaly, self or mixed anomaly between these 2 U1 symmetries. And then this is the principle to enables symmetric gapping term in the system. By one way to see that is you can one can try to bosonize these fermions and write down a Lartinger liquid theory, and then try to think about what are the symmetry allowed gapping term in terms of this cosine, in terms of condensing these vertex operators. And the condition for this vertex operator to fully gap out the system is, first of all, they should be mutually boson, and then they should also span the maximum Lagrangian subgroup, meaning that you should, in this 4-mode system, you should condense 2 vertex operators. And then this is actually the way to define the gapping term.
Can you say what's the nature of the phase?
After gap out the fermions, it becomes a short range entangled.
So it's just
trivial phase, yeah.
So when we map the Fermi surface anomaly to the language of this eminent symmetry, is it mix U1 cross U1?
Yeah.
For this example, take the charge 1 fermion, take 3 of them from the bound stage, and then your Fermi surface will fit like that. 3, they just have to pocket and overlap.
Yeah. That's yes.
And this 0 total Fermi Born condition is basically true.
Nesting condition.
That kind of thing is always possible.
Yes.
Why do you need all?
Yeah. So it's secretly you fractionalize the fermion, but if you combine them together, it becomes a very ordinary gapping problem. Yeah. Okay, in the last 5 minutes, I will quickly maybe go through higher dimensional examples where you can also consider Fermi surface symmetric mass generation happening in 2-dimensional or higher. For example, in certain lattice models which involve square lattice, fermion, spin-4 fermion hopping on the square lattice, where the fermion carries spin 1/2 degree of freedom on every layer, and then there's only one interaction, let's say, in this toy model, which is spin-spin interaction across the layer. In the weak coupling limits, you just have 2 independent decoupled square lattice fermion with this Fermi surface. So the Fermi surface is 4-fold degeneracy, 4-fold coming from the layer and the spin degree of degeneracy, degree of freedoms. But in the strong interaction limit, this model can also give you a gapped trivial product state. And the reason that it can end up with this trivial state is indeed because this Fermi surface anomaly, if you compute that, it's fully cancelled in this model. So this is an interesting model to study. And then the strong coupling limit, we know it's an insulator, and the weak coupling limit is a Fermi liquid. We want to understand the intermediate phase diagram. And then there can be two scenarios. Either you can have a direct transition between these two, or maybe there's an intermediate symmetry breaking phase setting in. It turns out that our analysis shows that it's the second case, which is less interesting. Although we originally wish it can be the first case, but maybe we need to change this Fermi surface shape in order to avoid all this nesting effect. But anyway, we can compute, for example, on the mean field level, that this intermediate phase, if you look at this there's an intermediate U1 symmetry breaking phase correspond to charge 2 condensation superconductivity, where its TC actually first grows with the interaction on the BCS branch and decays with interaction on the BEC branch and undergoes an XY transition and into the symmetric insulating state. So here, this is basically a superfluid transition of bosons, because if you start from the insulating phase, it's already forming Cooper pairs, singlet Cooper pairs on every site, and then you can treat that as a multi-insulator of Cooper pairs, and once you have some, once the interaction becomes weaker, then it allows some fluctuations of Cooper pairs on the lattice, so it's very natural to expect that there's a pair condensation that leads to superconductivity. One can also ask, if we go away from the half filling, so previous phase diagram is half filling phase diagram, that you can have this insulating phase, but once we deviate from half filling, you can no longer have this insulating phase because the Fermi surface will not be, the Fermi surface anomaly will not be canceled, and then you will have, basically you can imagine that the superconducting phase will extend to the whole phase diagram. The vertical axis is the filling fraction. If filling fraction is 0 or 1, that will correspond to band insulator. At 1/2, there will be SMG insulating phase. But away from that, it's all superconducting, basically. But there's a BEC region and a BCS and BEC region. And we can see this color correspond to the TC, and then TC is highest when the filling fraction is around 1/4 or 3/4. So then, last year I visited China and heard about a news that there's a new superconductor of 80 Kelvin transition temperature discovered in Meng Wan's lab, which is nickelate superconductors. So nickelate superconductor is actually a new family of superconductors, nickel-based, which also goes beyond the liquid nitrogen temperature. It has 80 Kelvin TC. And then the key physics there is that there's some two bilayer structure, and then the nickel atom actually forms a square lattice on a bilayer system. And then the key feature, the key ingredient there is that if you look at the orbital filling, then the d orbital, there's a dx squared minus y squared orbital, which is quarter filled. So that quarter filled d orbital is very peculiar to us. Then when we analyze this model more carefully, we will see that this quarter field dx squared minus y squared orbital, which is around the Fermi surface, actually has a hopping model, and then it can also have an interlayer spin-spin interaction, exactly the same model that we just discussed previously. So we can apply the same phase diagram to understand the superconductivity. And the nice thing is that the quarter filling nature actually sets the system along this line. So that's why you can imagine that there can be a very high TC in this system. Okay, so in summary, I tried to talk about how to classify Fermi surface anomaly. So the conclusion is that if you have a Fermi surface of co-dimensional P, then the corresponding classification is correspond to a SPT classification in P-dimensional space-time. And then using this idea, when you cancel the Fermi surface anomaly, one can have this phenomenon of Fermi surface symmetric mass generation, meaning that you can use interaction to gap out the Fermi surface into a trivial gap phase without breaking symmetry, and without maybe developing topological order. And it has implications on lattice regularization of 3450 chiral-fermion model, which is that one plus one dimensional model I just mentioned. And then it may have applications to nickelate superconductors. One thing I didn't have time to talk about is that the Green's function will also exhibit zeros along the Fermi surface in this Fermi surface SMG phase. And maybe in the future, we can think about how to match Fermi surface anomaly with topological order. I think that would be more interesting. So with that, thank you for your attention. Yeah.
Questions?
Okay. So, yeah, you can pass this.
Yeah, could you go back to the slide with the Fermi surface anomaly formula?
Oh,
yeah, that one. So it seems like if the index is not z value, but like zn value, this formula is not really well defined, is it?
Yeah, so the index should be like a zn valued, and then.
No, but if it's zn valued, you can't just put it into this sum and get it.
So roughly, this is a. Yeah, that's true. Then if it is zn valued, you should treat this index, maybe normalize it as 1 over n. Then you can also put it into this formula with mod 1.
But why does
this
mod 1
1
still?
is very subtle. You need to treat that differently when it is zn value. It becomes zn period, not the z period. Yeah.
I'm trying to follow the story about the mass term. So is this the input in the theory, which you kind of put in by hand and hold it, or it can be calculated self-consistently?
It's put in the theory. It's the starting assumption.
I see. So. And so then you can also make it to be temperature dependent to mimic the smearing of the Fermi surface.
That's true.
Okay.
In a
so
more complete theory,
okay.
it should be dynamical.
Okay.
But yeah.
And another one, a quick one. So your 6 fermion interaction does not conserve the particle number.
It conserves the U1 symmetry, which is not the particle number, because the particle number here is because A is charge 1 under U1 and B is charge 3, so you really need to annihilate 3B.
So they're not the original fermions, but some linear combinations of the original fermions.
Yeah, that's possible. That interaction, linear combination. You mean these fermions will mix under the interaction?
Well, but are these C's with A and B indices, are they the real fermions that we started with?
They are the real fermions we started with.
Then why is the number not conserved?
It is just these real fermions so you should really think these A and B's are like a U1 subgroup of maybe SU4 symmetry, where the charge assignment is not 1 for every fermion. Some fermion has charge 1, some fermion has charge -3. Something like that. So they are not electrons. Yeah. Yes.
Sorry, maybe you can go over there. Maybe Masaki?
Okay.
That's very interesting, but I got a bit confused because so you said there are 2 ways to implement this non-commutative geometry, background track or derivative.
Yes.
And I thought you started by using these background tracks, then you got the next stage.
Yeah.
But then at some point, in order to explain the dimensional reduction, you replace this derivative with dx and x.
Right.
So I thought somewhere you switch from this background transformation to this.
Yes. The point is that you can always switch between these two formulations because they should give you the same answer. It is just some answers are easier to get in one formulation. Some conclusions are easier in the other formulation. That's why we just choose our way of resolving this non-commutativity for the purpose of getting our answer.
So you can start from derivative.
Yeah, if you. Yeah, for example, if you want to derive the edge modes on this phase space Chern insulator, it's much more easy to use the derivative trick other than considering a magnetic field in the phase space, then you need to solve Landau level problem. But if you use derivative, there's a more easy algebraic manner to get the same result eventually,
Yeah, for this 3450 calculation, you show there can be gap. My question is that whether that example have a Z16 anomaly or not, or maybe have no Z16.
That case, it's the anomaly classification should be Z. The anomaly classification should be Z cross Z, I think, because it has two U1 symmetry. That example is not the Z4 case.
Okay. So
yeah.
I see. Now I see. So in that case, it's anomaly free. So
it's just anomaly free because of the design.
Okay.
Yeah.
Thank you.
Oh. Yes, you can think of it as a generalization of that. Yeah.
So how do I pick up the Zn nature in that case? Because any integer filling is trivial from the lattice perspective.
Yes, but sometimes maybe you have 1/4 filling, and then maybe you are wondering whether that is actually gettable. But in some cases, when it's classification Zn, those 1/4 or fractional filling, integer, a rational number filling, you should further analyze it, whether that actually cancels the anomaly. Yeah.
Last question.
So going back to your original formulation in the momentum space with this magnetic field. So usually when we talk about SPTs, right, we want the interactions to be local in space.
Yes.
So, but here your space contains both space and momentum.
Yes.
So why should interactions be local in momentum space?
So interaction is no longer local in the momentum space. And if you look at the careful analysis of Chongming, then they define how to why the momentum space should be treated as negative dimensions precisely because interaction is not local in the momentum space. It is using the locality of interaction to define which dimension belongs to real space and which belongs to momentum space.
Thank you.
Yeah.
Okay, so let's thank the speaker again.
Thank you.